All right, good afternoon, good morning, everybody. This is February the 14th. Happy Valentine's Day to everybody's watching the recorded version of this lecture. Exam 1 announcement. So the Exam 1 window ended yesterday. In general, I don't extend windows on exams unless there's some extreme extenuating circumstance. So anyway, just wanted to kind of point that out. I intend to try to have these graded and posted by Sunday or Monday. So I'm going to say Monday right now. So I will post grades on your WebAssign gradebook. And I would say right now we'll go ahead and say that that will be by Monday, February the 19th. It's possible that they could go up earlier, but I just don't know right now. I don't even have all of the exams. I only have right now probably about maybe a half of them. When I post them, I will send a remind message out to everybody that they are posted and they can go in and look at those. Also, remember, if you want your graded exam 1 back, and I'll remind you about this again next week, but if you want the copy of your graded exam 1, email me and I will send you an email back with your graded exam 1 attached to that email. WebAssign announcements. You did have, I've changed a few due dates here. I've extended a few. Sections 3.3 and 3.5, I did have due on February the 18th, and I've extended those for 3 days. So you've got a week to do those, 3.3 and 3.5. We'll finish up all that material on those sections today. So you'll have a week to do those assignments. So those are now due February 21st. And then 4.1's assignment, I pushed that back also to February 25th. And so, kind of keep track of the due dates and don't get behind on WebAssign. And then today, what we're going to do is we're going to finish up 3.3. And actually, I have 3.4 there, but it actually should say 3.5, I guess. That's function transformations. And then that will finish up 3.3 and 3.5. And then we'll hopefully get started on linear functions today and get some basic things done there. And then that will put us in a position for next Monday, and this is my goal for next Monday, is to cover what's left of linear functions, so finish linear functions, and then start in on, or not start in, but also finish quadratic functions. And start in on our kind of look at polynomial functions specifically. So we're going to finish quadratic functions next time also. So that's our goal, is by next Monday to have finished quadratic functions. So I think we're in decent shape to do that. So, all right. So I want to go ahead and get started. I know that there's some increasing, decreasing function material on section 3.3 in your WebAssign homework, so I wanted to cover that. That's something we haven't talked about yet. I'm not going to make a huge, immense big deal about this, but I would like you to have some idea of what we're talking about when we are looking at functions that are increasing and decreasing. Increasing functions, a function is increasing quite simply if the x values are getting bigger as you go from left to right. So x's are getting, I'm sorry, not the x's. That would be, they're always getting bigger as you go from left to right. I'm sorry. The y's are getting bigger. That's much better. As you go from left to right. It's always left to right when you're looking at increasing and decreasing functions. So y's are getting bigger as you go from left to right. And a decreasing, and by the way, decreasing functions or increasing functions rather, another word for that is simply that it is a rising function, right? So when you think of increasing functions, when you think of those words, increasing functions, think about a function rising as you're going from left to right. Those mean the same thing. And when I say rising, what that means is that the y values are simply getting bigger. All right, and then we have decreasing functions. Similar, very similar here, but now what's true? The y's are getting smaller. Again, obviously, as you go from left to right. And in this case, you're talking about a graph that is falling as you're going from left to right. So those things go together. When you see decreasing functions, you are talking about a function that is falling as you're going from left to right. All right, so how do you talk about that, and how do you report that to somebody when you are looking at a function and trying to analyze it? So how do you write those kinds of things down? All right, so we're going to look at a function and look at a basic function right now, and we'll look at something a little bit more complicated in a minute. But let's look at a parabola that looks like this right here, where it has a vertex here at the point 3, 1. Well, as you're moving along the x-axis, and this is very much like what you would have done with the domain a minute ago, or not a minute ago, but over the last couple of weeks. When you were looking at domains, what were you doing? You were walking along the x-axis from left to right. Well, you're doing the same thing here. And as you walk along, what's happening here, as you look at x values, again, you remember you're going from left to right. Look what happens to the y values. Like at that x value right there, you've got a y value right there. At this x value, you've got a y value right there. And what's happening to these y values? What's happening to the graph? It's falling, right? And so what we say is that this graph is decreasing for all x values from -infinity to 3. It is a falling graph over this interval on the x-axis. I'm actually shading this on the x-axis. Now notice that at 3 itself, the graph seems to have bottomed out at 3. That's actually a minimum value. I'm not going to make a big deal about minimums and maximums, but the graph does reach a low point right there, right? And so you might actually delineate that point there. In other words, identify it with like a vertical line and say, hey, at that point, at that x value, at x equals 3, the graph seems to bottom out. So what happens? The graph is decreasing before that. It's falling in this interval, right, up until x equals 3. And then what happens after x equals 3? Now the y values start getting bigger again. And so now we say that the graph for these x values is rising. And so we say that the graph is decreasing, like I have it written here, from -infinity to 3. You always put in a parenthesis around the -infinity. And then around the 3, that minimum value, what I'm going to do is just agree, and different textbooks will actually define this differently, to be honest with you, but what we'll say is we'll just put an open parenthesis there and say that for all the x values before 3, the graph is falling. At 3, the graph is bottomed out, right? And so we won't include 3 in this set. And we also won't include it where it's rising either, right? So you have the graph is increasing from 3 to infinity. And notice I put a parenthesis around the 3 also, because we're not going to include 3 in either one of those sets. Because it doesn't make any sense at that bottom point to say that the graph is falling there or rising there. That's the place where the graph has stopped rising or falling, is the way I would look at it. All right, so that's what you would do to identify where a function's increasing and decreasing. So identifying these high points and low points, I believe, is the way to approach this kind of situation and help you kind of keep straight on a graph that's maybe a little bit more complicated. So let's look at this graph, and let's see. So let's say we have a graph. Maybe this one's a little bit more complicated. The graph comes down like this, and then it rises and falls like that. And so once again, let's identify these high and low points on the graph. And so there's a low point right here at where I'm putting that red dot right there at -3, 1. And so we'll put a vertical line through that low point. Right, that's a minimum on the graph right there. And then at this point right here that I'm going to identify with the green dot, there's a high point right there. There's a maximum on that graph. So drawing in those vertical lines is, I think, is a good idea to identify where the graph has a low point or a high point. And then what happens if you identify all those places, then in between, the graph is either rising or falling. Right? So so I start identifying the intervals on the x-axis. And so what's the graph doing right here? Right, as you're going from, remember, always from left to right, the graph is falling right there. Right, so that means that the graph is decreasing. And then between that vertical red line and green line, what's happening? The graph now is rising in here. So we write rising in there. And then finally the graph starts to fall again. When you're writing where it's increasing and decreasing, you are identifying this by x values. So that notice we will always be moving along the x-axis from left to right, always along the x-axis, and looking at the x values where the function is rising and falling. And so on this function, we would say that f is rising or increasing. And I've got the little interval sketched out on the x-axis there, right? And it would be from -3 to 0. And notice I put parentheses around the endpoints. We're always going to put parentheses around these endpoints for this kind of problem. And then f is decreasing or falling. And again, we have the intervals drawn out for us. And where is it? It's from -infinity to -3. And then again from 0 to infinity. And so f is decreasing in that interval. All right, so identifying the places where the graph is got low points or high points, drawing vertical lines through those points, and then identifying the intervals on the x-axis, I believe is a good approach for this kind of problem. All right, so let's look at another problem here. And maybe something that's slightly more complicated. And let's see if we can identify these spots. So here's my graph. Whoa. And by the way, we will be looking at graphs that look like this one as we start dealing with polynomial functions. Okay. All right, so let's identify these high points and low points on the graph. And so you've got a low point right here. We'll draw a vertical line through there at x equals -4. And then we have a high point right here, and that's when x is equal to 1. And then we have another low point right here, and that one would occur at x equals 2. And so notice those vertical lines divide up our x-axis in these nice little intervals where we can identify where the graph is rising or falling. Right? So the graph is going to be falling in this interval, and then rising. If you've marked the high points and low points, then the graph will always do the same thing in between those high points and low points. It'll either always be rising or always falling. So in this interval, the graph is rising. I'm trying to use some color here to kind of make these intervals stand out as being different. And then this next interval, the graph again is falling right there. And then finally, in the last interval, after x equals 2, the graph is rising. And because of those arrows at the end of the graph, right, these arrows on these intervals continue on forever, so you've got all, going off to the right forever, and you've got going off to the left forever here, and there should be an arrow like that also. And so, not a bad thing to think about here. So what do we have here? That f is increasing or rising in the interval from -4 to 1. We're going to use parentheses there. And then also in the interval from 2 to infinity, right? We've got the nice little intervals marked off on the x-axis there. So I think that's a way to approach it. And then f is decreasing. F is decreasing from -infinity to -4, right? That's where it's falling. And then again from x equals -1 to 2. And I do have a little bit of a sign error there in that one minimum value I realized is at x equals -1 right there. And so that does change a little tiny bit here. I have to go back and fix these things. F is increasing from -4 to -1, and then again from 2 to infinity. Yeah, now it's right. And then decreasing from -infinity to -4, and then also from -1 to 2. All right, so drawing out those intervals, I think, is a great thing to do to identify where a graph is rising and falling, and then writing that out. And to identify these intervals, always take the graph and look at where it's got high points and low points, and that will help you to sketch these things out. Now, if you have a graph that has asymptotes in it, and this will be like my last example here, that doesn't really change anything about how you would approach the problem if it has some kind of an asymptote in it. So if you have a graph that maybe looks kind of crazy, like this one right here, comes in like this, and then the graph looks like that. Now, and it's got a vertical asymptote here at x equals -1. Don't do anything different. So here's the asymptote right in here at x equals -1. Don't do anything different from what I told you on the last couple of problems. Identify the high points and low points. Now, what gets students confused on this problem sometimes is they identify more high points and low points than there really are. This graph only has one low point. Right there at x equals -2 is a low point. And in fact, there are no other high points or low points. That's it. That's a low point on the graph right there. And at x equals -2, and there aren't any others. The graph levels off right in here, at this point right in here on the x-axis, but it never has a high point or a low point there. And so what do we have here is that the graph is falling in this interval, this blue interval right here, right? And then there's an asymptote, and then it starts to rise, and it's rising in this interval. Kind of stick it in here. It's rising in there. And let's see, since it's a small interval, I'm just going to write the word rising there and put an arrow like that. And then what happens after the asymptote, the graph continues to rise after this. It doesn't start to fall again. It just continues to rise. So it's still rising in this interval. So this one looks a little bit different, but you're not really doing anything different. Don't make it. It actually ends up being easier than what we've been talking about in some ways. So f is increasing or rising from -2 to the asymptote, which is at -1. Don't include the asymptote in here at all. and then from -1 to infinity. Notice how we left out -1 because -1 is where the asymptote was. And then f is decreasing from -infinity to -2, like that. All right, so there are a couple of really good examples now for increasing and decreasing. And so, so that takes care of that. You should be able to deal with those WebAssign questions. And those of you who are watching me live today, obviously you guys know what to do. Shout out if you have a question, but I'm not hearing anything. So I think we're probably okay on that. All right. So our next stop here is to look at function transformations. Go back and look at these again, and look at what I would say is function transformations part 2. We did part 1 before the exam, so this is function transformations part 2. And so what I'm going to first do is write down the transformations again, and then we're going to identify some basic functions, and then we're going to look at some transformations of those basic functions. All right. So the function transformations that we talked about and introduced before the exam, we introduced the shifts, right? And that's one type of transformation is what we call a shift. And the shifts can be horizontal or they can be vertical. And if they're horizontal, then it depends on how the function is written. If it's f of x plus k, notice that we're adding a k value to the x value. We're messing with the x value here. Since we're messing with the x value, that means we're moving the graph left or right, because that's how what x controls, right, is your distance left or right. So we're going to say that k is always positive here. So if you have f of x plus k, then that is a shift to the left. And if you have f of x minus k, that is a shift to the right. Notice it's kind of backwards what it seems like, because when you add the constant, you're shifting the graph back to the left. When you subtract the constant from the x, you're shifting the graph to the right. And then we have what we call vertical shifts. And the vertical shifts are when you mess with the y value. And remember, the y value is f of x. That y and f of x mean the same thing. So you have a vertical shift if you have f of x plus k, and that is a shift up. And you have a shift down if you have f of x minus k. Notice what you're doing here is you're not subtracting the k value from the x value, from the x value. You're subtracting it from the function itself, and the function represents y. So what you're doing is you're adding a constant to y, or you're subtracting a constant from y. So that's what we call the vertical shifts up and down. So those are the shifts. And then we have the reflections. Reflections, we have talked about 2 reflections here. You have a reflection around the x-axis. Sometimes students will refer to that as a flip of the graph. You're literally flipping it upside down. And you get a reflection around the x-axis when you are looking at negative f of x. And again, remember what f of x represents. It represents y. And so what this is really saying is change the sign of y, right? If you change the sign of the y value, you're actually taking the graph and you're literally flipping it vertically. You're flipping it around the x-axis. And then you get a reflection around the y-axis. So that means a reflection left and right if you are changing the sign of the x value. And so that's f of negative x gives you a shift around the y-axis, because that's saying change the sign of x. All right, so those are the reflections. And then finally we have what we call the changes in shape. And I've classified those as two groups, and those are stretches and compressions. And a stretch or a compression you get with multiplication by a constant. And remember, if k is positive, then you have k times f of x. What are you doing there? You're multiplying. Remember what f of x represents. It represents y, right? This is really important to always keep in mind that when I write f of x down, when I write that symbol down, I'm talking about a y value. And so what is this stretch saying? It's saying you're taking a y value and you're multiplying it by k. And if k is bigger than 1 right here, you get what we call a stretch. And this is multiply the y value by k, whatever the k value is. And you get a compression. And so what does that do? That stretches the graph away from the x-axis. It literally kind of pulls it away from the x-axis. And then if you have k times f of x, but the k value is less than 1, and remember, we're talking about the k value being positive, so we're just going to say the k value is less than 1 here, or you could say that k is between 0 and 1 if you wanted to, right? Then what's going to do, you're still multiplying the y value by k, but the k value is now smaller than 1, so it makes all the y values smaller, right? And so that's a compression, right? Again, you're multiplying the y values by k, whatever k happens to be. Now, we are not going to be looking at stretching or compressing the graph horizontally. These are all vertical stretches or compressions, and I'm not going to look at the ones that go horizontal at all. We're just not going to deal with that type of function transformation. So these are the transformations that we're going to look at: shifts, reflections, and changes in shape. All right, so now remember what we've done so far is on part 1 of this function transformation stuff, we looked at what if the basic function was a some kind of a basic graph, and I gave you a graph, right? So let's say that the graph maybe, and we are not going to look at anything too terribly complicated when we do this, but let's say that our basic graph looks like this one right here. It has this line segment like that, and then like so. So a little kind of upside down V shape like that. All right, so if that's our basic function, and so I'm going to identify this as the basic function. Right, and so like on an exam, I would give you a graph like this and say, hey, this is your basic function, and then I would give you some transformations of that function to sketch, and we'll call this basic function f of x. Then if I ask you to sketch f of x minus 2 plus 3, then that would be the f of x minus 2. The x minus 2 would shift the graph to the right 2. And I might ask you to actually write this out in words, right 2. And then the plus 3, you would shift the graph up 3. Right? So not a bad idea to actually be able to write out those transformations in words. That's something I might ask you to do, is to actually identify them that way. And so you're literally taking the graph that you've got, and so I'm going to sketch it again. And let's see. And what I would do is, if I did it this way, is I would go ahead and draw this in as a dashed line, because that's not our final graph here. And then what are we doing? We're literally moving the graph to the right 2 units and up 3 units. And you're literally, every point on the graph, you're going to the right 2 and up 3. So what you're doing here, like this point right here, is shifting to the right 2. It's right 2 right there, and then up 3. Now, if we did that for every point, it would get really messy. And so I'm just going to start with that point right there. And every point gets shifted exactly the same way. And this would be your shifted graph like this. Right? Every point has been shifted up 3. I'm sorry, to the right 2 and up 3. To the right 2 and up 3. And that would be our transformed graph, right? And this would be the graph right here of f of x minus 2 plus 3. Right? That's the kind of thing we were talking about last time. If we, let's see, if we did this, let's go ahead and do one more. Let's do a stretch compression kind of reflection kind of thing here. So let me go ahead and sketch in one more time the basic graph. So there's our basic graph right there. And in this case, I wanted you to sketch -3 times f of x. All right, -3 times f of x. This is a multiplication problem. The negative sign is a reflection. Right, when you have a -1 sitting in front of the function, it means you're changing the sign of y. And so that's a reflection around the x-axis. In other words, it's turning the graph upside down. And then the 3 is representing a stretch of the graph. It's a multiplication problem, and it's a stretch by a factor of 3. So stretch by a factor of 3. And so that means take all the y values and you literally multiply them by 3. You literally multiply them by 3. So there's actually two things going on here. You could do both of them at the same time, but what I'm going to do is I'm going to go ahead and do the stretch first, and then I'll do the reflection. Right? I'm going to kind of take my time and do this in separate steps here. So look at this point right here. This point on the far left is at the point -3, -1. And so what do? We multiply the y value by 3. Notice the x value stays the same. We're multiplying the y value by 3. And so the new y value would be at -3. So it'd be -3, -3. That's our new point right there. Notice that this y value on the x-axis is at -3, 0. And when you multiply that y value by 3, it stays 0. So points like that on the x-axis don't move anywhere. And then the next point is here at -1, +1. So -1, +1. And so when you multiply that y value by 3, you get -1, +3. Right? Here's our new point up here, -1, +3. And so notice you are getting this first line segment is stretched away from the y-axis, and it kind of looks like I've got right there. And then you continue on to do the same things. Remember that y values that are 0 stay 0, and so points on the x-axis stay there when you've got a stretch or a compression. And then this last point would get stretched from 1, -1 to 1, -3. Multiply the original y value by 3 again. And so here is the graph stretched vertically like that. And then finally, now remember, that's our stretch vertically. So that graph in blue that I've got there, I guess maybe should have been a dashed graph, but I'll leave it as a positive, as a solid line there. That's not our final graph. That is the graph of 3 times f of x. But what am I graphing? In this problem, I'm graphing -3 times f of x. And so you'll literally flip this graph around the x-axis. In other words, you change all the signs of the y values. And so this ends up being my new graph. You're literally flipping it around the x-axis. You're turning the graph upside down. And so this is our final graph right here. Like so. And that's the graph of, in heavy red there, is the graph of -3 times f of x. So that little graph that I had there was that dashed graph is my original function. And then I first stretched it. And so here's my stretch right here. Put put that in red, or put it in blue rather. So this is my stretch. And then finally, the negative sign, this is my reflection. Okay, so this is what we talked about last week. You have some examples here, and I am going to email everybody out. I don't remember, to be honest with you, if I did this last week or not, but I'm going to email you out some practice problems on this kind of transformation, where you're given a graph as your basic function, and then you're expected to transform it. And so I'm going to give you some practice problems on that, so that you have more problems that you can practice going into exam 2. All right, since this is going to be your first major topic on exam 2. All right, so that's function transformations part 1. Now, function transformations part 2, the basic function is no longer going to be given as a graph. It's going to be instead given as an equation. And so what we do here is we identify a group of basic functions. And those basic functions that we're going to talk about at this time are f of x equals x squared, f of x equals x cubed, f of x equals the absolute value of x, and f of x equals the square root of x. And I believe I may have graphed these at the end of the last lecture, but I'm going to go back over these all again, and we're going to be talking about transformations of these kinds of functions. So let's start with the square function, f of x equals x squared. So this is sometimes called, like I said, the square function. And the graph for our square function is a parabola. And in particular, the vertex of the parabola is at the origin, and the graph goes through these key points here. It goes through the point negative 1, 1, and 1, 1. And you've got a graph that looks like this. Right, notice that the domain for that function is negative infinity to infinity. The range is bracket 0 to infinity. And also we can identify that this is an example of what we call an even function. It has symmetry with respect to the y-axis. You can also talk about where the graph is rising and falling, where it's increasing and decreasing. So that would be the basic function. And so if we were looking at transformations here, this is the way we would be looking at this, is you would be given these instructions, and that would be to sketch f of x equals x plus 3 squared minus 4. F of x equals x plus 3 squared minus 4. All right, and so that transformation, what am I doing there? I am messing with the x value, the x plus 3. And just like we saw on the last page, that x plus 3 then would shift the graph to the left 3 units. And then the minus 4 would shift the graph down 4 units. And the basic graph, what we do is we identify that the basic graph is our square function, right? That the basic function is this parabola like that. So if I were to give you this problem, right, you'd kind of walk yourself through those 3 basic ideas. You'd identify the basic function, and you'd identify any transformations that are involved. And then you'd sketch the graph. So this is what we're doing here. Now, if you want to, you can make a quick rough sketch of the basic function on your coordinate system. That would be okay to do. And a lot of students, that's the way they'll approach this, is they'll first make a sketch, a light sketch of the basic square function. Here's our basic square function. Like this. And then they'll shift the graph. Now, when there's shifts involved, what I frequently see students do, and this is a good idea to do, is they actually sketch in the shifts by actually moving the axes. And so notice they sketch a new y-axis, and notice what I've done with that y-axis is I've taken the original y-axis and I've shifted it left 3 units. And then they take the x-axis and they shift it down 4 units, like that. This is a good frame of reference here to sketch in this new coordinate system. And then what are we doing here? We are simply sketching the square function on that new coordinate system. And here's our square function sketched on that new coordinate system, right? Where you identify the key points on the graph, and maybe do a little bit better job sketching that. Maybe a little bit better there. Right, and that would be our transformed graph right there. Right, notice it's been shifted to the left 3 units and down 4 units. You may be asked to write the domain and the range for these kinds of problems, so don't panic if you're asked for that. Notice the domain here is still negative infinity to infinity. And the range, though, is different because the graph has been shifted down 4 units. The range is now from -4 to infinity, like that. And we've got our first transformation of the square function sketched, right? We've got it put in right there. All right, let's look at, I'm going to look at a simple one here with the space that I have left. Let's sketch f of x equals the negative of x squared. And so what does that negative sign do, right? When you stick it in front of the function, right? If it goes in front of the function, then that is a reflection around the x-axis. Reflection, x-axis. And so this is a flip of our graph right here. Right? So if you want to, you could sketch in the basic function, which is the square function, right? Identify that the basic function is the square function. Do a decent job plotting the points here. I'm going to look to make sure that this graph that you've got goes through these key points, okay? And then literally you're just flipping this thing upside down. And so this is a pretty easy transformation to sketch. You're literally taking the parabola and flipping it around the x-axis. And here's the graph right here. And that graph is a reflection around the x-axis. The domain on this graph is negative infinity to infinity. The range has been, since the graph has been flipped, the range is from negative infinity to 0 with a bracket like that. All right, and so that's our transformation, right? It's a reflection around the x-axis. All right, let's continue on. Here, let's look at another problem. And so we're going to continue talking about f of x equals x squared, right? That's our basic function. And so we want to sketch next f of x equals, let's say, 3 times x minus 2 squared. 3 times x minus 2 squared. All right, so if we're going to sketch 3 times x minus 2 squared, then first of all, let's identify what's going on here. Let's see. So we've got the x minus 2. Well, first of all, our basic function is the square function, right? So f of x equals x squared. And so you think about what the basic function looks like. It's our parabola that goes through the origin. All right, just make a little quick rough sketch there. And then the x minus 2 would shift the graph to the right 2, right? We're subtracting something from the x value, and so that would go to the right 2. And then the 3 would be a stretch of the graph by a factor of 3. Now, if you think about order of operations, the order of operations on this problem are that the x minus 2 is first, right? And that's a shift of the graph to the right 2, and then the 3 is the stretch. Now, as it turns out, you can really interchange those transformations, and you'd still have the same graph at the end. I'm going to try to go ahead and obey order of operations here and do it in the order that we've got the operations going on in a particular problem. But it turns out that if you switch the order of those, you end up with the same graph. So here's our basic graph, is our square function. And so what am I going to do? I'm going to first shift that graph to the right 2 units. All right, so here's my shift to the right 2 units. And if you want to, you could, it gets a little bit cluttered, but I could sketch in the shift as a new coordinate system. There's not a shift down, so notice the x-axis doesn't move at all, but the y-axis moves over to the right 2 units. And then so here's my shifted graph right here. Right, and so this is just, the red graph is x squared, right? And then the blue graph here is x minus 2 squared. Right, it's been shifted to the right 2 units. And then finally, the stretch by a factor of 3 says take these points right here, look at the y values on those points, and the y values in both cases are 1, right? So like this point right here is at the point 3, 1. So you multiply those by 3, and you're up here at 3, 3. And so in both cases, the y values are 3. The vertex, its y value is still 0. So notice what happens is that when a parabola has been stretched like this, it makes it look like the parabola is narrower. It's really not what's happening. The graph is literally being pulled away from the x-axis. So it kind of gives the illusion that it's being made narrower. That what's happening is each y value is being multiplied by 3. Right, and so that's our stretched graph right there. All right, so let's continue on this process. So let's move on to the cube function, f of x equals x cubed, and look at some transformations there. So the cube function, and I believe I've talked about this on the last lecture, I'm not 100% sure, but the cube function goes through 0, 0, it goes through 1, 1, and it goes through -1, -1, and has this shape. Like this, and that's our cube graph. And those are the 3 key points on the cube graph. All right, notice that the domain for this graph is all reals. The range is also all reals because of those arrows there. And this is actually an example of an odd function, right? It's an odd function because it has symmetry with respect to the origin. And so that's what we call an odd function. All right, so let's have a look at a transformation. So let's sketch f of x equals negative x plus, let's say x minus 4 cubed minus 5. F of x equals the negative of x minus 4 cubed minus 5. All right, so we identified that the basic function is the cube function. It's f of x equals x cubed. So this is the graph we're starting with, right, is our graph of our cube function. That's my quick sketch there. And then what happens here? The x minus 4 shifts the graph to the right 4. The minus 5 shifts the graph down 5. And then finally, that negative sign at the front is a reflection of the graph around the x-axis. So you got 3 things going on here in this problem. All right, so I'm going to make a sketch of the coordinate system here. Give myself some room. All right, so here we're going to sketch in our basic function, which is the cube function, right? So here's, make it a lightly sketched graph, so I make it dashed or dotted. So there's the cube function right there. And what we are doing is we are shifting the graph and then reflecting it around the x-axis. So I'm going to shift, and technically the order of operations here are that the graph shifts right 4, then it reflects, and then it's a shift down 5. So that's what I'm going to do. I'm going to do right 4 first, then reflect, and then shift down. All right, so here's my my new coordinate system if I want to sketch that in. Here's my shift to the right 4 units. I'm also going to have a eventually reflection down here at this point. And really, if okay, so let's see. So my sketch or my shift to the right 4, here's my shift to the right 4, like this. And then what do I do with that graph? I then reflect it. And so I'm going to kind of try to color code this a little bit. So this would be the reflection this way around the x-axis. Right, so in blue, I've got x minus 4 cubed. And then in green, here I have the negative of x minus 4 cubed. And you can see how the order of operations works. And then finally, the minus 5 shifts that final graph down 5 units. And so here's my final graph. I'm going to make this one heavier as far as the drawing goes right here, and that's my final graph. And so that's the negative of x minus 4 cubed minus 5, like that. Notice it going through these same 3 key points on the shifted graph at the end, so kind of keep that in mind as you're getting to the final graph here. All right, so there's the cube function and a transformation of the cube function. Let's now go on to the absolute value function. F of x equals absolute value of x. The graph for this function, recall, is kind of a V-shaped graph. So it goes through 0, 0, it goes through 1, 1, and it goes through negative 1, 1. Like that. And you have this V-shaped graph here. And this is, so it kind of reminds you in some ways of the parabola, right? But it's a similar as far as its features go. So its domain is all reals, negative infinity to infinity. The range is from bracket 0 to infinity, just like the square function. And then this is also an example of an even function, right? It does have symmetry with respect to the y-axis. So there's our basic graph for the absolute value function. So if we look at a transformation of that function, so let's say we are going to sketch this transformation. Let's say we have f of x equals 1/2 times the absolute value of x, and then let's say that is plus 6. 1/2 times the absolute value of x plus 6. So we identify these basic ideas here. First of all, the basic function that we're identifying in the problem is that it's the absolute value graph, right? And so we know it's this V-shaped graph like that. And then the 1/2, the multiplication by 1/2, what does that do to the graph? That is a compression of the graph. That value, that k value is less than 1, and so that's what we call a compression. Multiply the y values by 1/2. And then finally, the plus 6 is a shift of the graph up 6. So writing down all those basic ideas, I think, is a really good idea for these kinds of problems. Kind of help you keep things straight. All right, so let's identify, first of all, the basic graph. We'll draw that in lightly. So here's our basic graph. We are careful to write in the key points on this transformation. So there's our absolute value graph. And then we're compressing that by a factor of 1/2. So these y values right here, you know, this this point, this key point here is at 1, 1. So when you multiply that by 1/2, right, you get 1, 1/2, right? And so that's that point right there is at 1, 1/2. And it's the exact same with the point over here at negative x equals -1. And then remember, these compressions don't mess with points that are actually on the x-axis. And so this compression kind of looks like this. And notice it makes the graph look like it widened here, right? When you've got this absolute value graph like that. Again, what's happening actually is the graph is being smushed in towards the x-axis. All the y values are being multiplied by 1/2, and so it's actually all the y values are only half as high as they were for the original graph. And then finally, we sketch in the vertical shift of this graph, which is up 6, 2, 3, 4, 5, 6. So I'm going to go ahead and, here's my vertical shift up 6. I'm going to go ahead and sketch in that x-axis. The y-axis wouldn't have gotten moved here. And then that green graph that I've got down there, I'm just literally moving it up to this new coordinate system. And so here's my new graph here. And notice I've got this compression has been taken care of as part of my sketch, right? That was my first step right there. All right, so this was 1/2 times absolute value of x right here. And then finally, 1/2 times absolute value of x plus 6 right here. Right, so we compressed the graph and then we shifted it up 6 units. Okay, let's look at another graph here. Let's say we have, let's sketch the negative of x minus 3 plus 4. All right, the negative of x minus 3 plus 4. So the basic graph in this case is our absolute value graph, right? Absolute value of x. So it's our V-shaped graph. And then the x minus 3 shifts the graph to the right, 3. The negative sign out front reflects the graph around the x-axis. And then finally the plus 4 shifts the graph up 4 units. All right, so let's have a look at this one, and let's see what we can do. Let's take our time. Let's write out all the steps that we need. We'll do this using order of operations. So, and by the way, the shifts on this graph are to the right 3 and up 4. So I'm going to sketch those in because that's where we're headed, basically, right? And so there's our shifts, and eventually we'll have the graph sitting up on that coordinate system. So our basic graph is the absolute value graph. I make a rough sketch of the absolute value graph. I shift it to the right 3 units. So the graph gets shifted over here to the right 3. Here's my shift to the right 3. And then the graph, using order of operations, gets reflected around the x-axis. And so the graph literally gets flipped upside down. Whoops, and let's go ahead and make that use a different color here. Excuse me, a different color. But this is still dashed because this is not my final graph. Right, and so notice I've got 3 steps here so far. You know, what do? We started with the basic graph, the absolute value of x. And then what did we do? We went ahead and shifted it to the right 3 units. And so this is the absolute value of x minus 3 right here. And then the green graph, we reflected that graph. So this is the negative of the absolute value of x minus 3. And then finally, we shift that graph up 4 units and put this on my new coordinate system, and here it's sitting right here. The new coordinate system gives me a good idea that I've got it in the right spot, and that's the negative of the absolute value of x minus 3 plus 4. Now I know it can be kind of messy, but if because you've got all these little intermediate graphs here, some students don't like to draw in those intermediate graphs, but I do think it's a good way to kind of keep things straight and keep the order of operations straight in these problems. All right, our next basic function, and the last basic function that we're going to talk about at this point is the square root of x. F of x equals the square root of x, square root function. So this one's different from the first three in that it has a restriction in the domain. Right here is our basic graph. It goes through 0, 0, and 1, 1, and 4, 2. And there's our basic graph right there, square root of x. The domain, like I said, there's a restriction on the domain. This graph's domain is bracket 0 to infinity. The range, also bracket 0 to infinity. And this is an example of a graph that's neither even nor odd. All right, so let's have a look at some transformations here. So let's sketch f of x equals 3 times the square root of x. All right, so a relatively straightforward transformation. That 3 is multiplication by 3. This is an example of a stretch. And what are we doing here? Remember, with the stretch, we are multiplying all y values by 3. Right, and so the square root function is a nice function to look at these stretches in because it I think, really kind of stands out as being something that maybe makes the stretches make a little bit more sense because of the shape of the graph. So I'm going to sketch in, first of all, our square root graph right here. Start off with, right? So you've got 0, 0, 1, 1, and 4, 2. And so remember, what we're doing here is we're taking all those y values and we're multiplying them by 3 to get our new graph, the stretched graph. So 0, 0 just stays at 0, 0. But 1, 1, it gets stretched by a factor of 3, and so now that point is sitting here at 1, 3. And 4, 2 gets stretched by a factor of 3. And so this is sitting here at 4, 6. Notice that the x values don't change. It's the y values that are getting multiplied by 3. And here is our stretched graph, is that blue one right there. Right? And so that is 3 times the square root of x. Where I took all the y values and multiplied them by 3. Now, you really think you can see the way the graph getting stretched in this case, that the word stretch really kind of is much more descriptive when you're talking about this square root function. Okay, so let's look at another transformation. Let's say we have f of x equals the square root of negative x. We haven't looked at this transformation yet with these basic functions. And so when you stick a negative sign in front of the x, remember what that does is that is a reflection, but it's a reflection around the x-axis, not around the y-axis, but around the x-axis. And so that graph, again, I think it's really a good idea to sketch in the basic graph to start off with. So here's your square root graph. There's square root of x. And so that negative sign in front of the x says change the sign of the x values. So let me do that in this problem, and let me show you what's happening here. So you have 0, 0, you have 1, 1, and you have 4, 2. And that negative sign in front of the x is saying change the sign of the x's. So if you change the sign of the x's, and let me write that, change sign of all x's, right? That's what a reflection around, whoops, I said reflection around the x-axis. I don't know why I wrote that. That's a reflection around the y-axis. Somebody would have yelled at me about that eventually, I think. And so if you're changing the sign of all the x values, right? So 0, 0 doesn't move at all, but 1, 1, the x value changes to -1, and so you're here at -1, 1. And 4, 2, the x value changes sign, and you're here at -4, 2. Notice that the y values don't change, it's the x values that change. And so this is our new graph, is this blue graph here. And notice this is sure enough, is a reflection around the y-axis, right? It's reflected around the y-axis. Flipped horizontally is another way to say that. Okay, let's see. So let's look at another, one last transformation for the square root function. Let's say we have the negative of the square root of x plus 3 plus 5. F of x equals the negative of square root of x plus 3 plus 5. So the basic graph here is the square root graph, right? And so we identify what the square root graph looks like so. And then the x plus 3 shifts the graph left 3. The negative sign in front of the square root, like that, reflects the graph around the x-axis. So reflect x-axis. And then finally, the plus 5 is going to shift the graph up 5 units. All right, so here's my transformed graph. Give myself a little bit of room here. All right, I first start off with my basic graph, the square root graph. All right, there's square root of x. And then I know that my shifts are left 3 and up 5. So here are my shifts. I'm going to go ahead and sketch those in at the beginning, because that's going to be kind of the target area for our graph. And so I'm shifting the graph to the left 3. All right, so here's my shift left 3. All the points just get shifted backwards. You just count literally back to the left 3 units. And so that's the square root of x plus 3. And then I take that graph and I reflect it around the x-axis. I literally flip it upside down. And so that graph gets reflected around the x-axis. And so this is my green graph right here. And so that's negative square root of x plus 3, like that. And then finally, that graph gets shifted up 5 units. I have the graph sitting up here, and I have my coordinate system sitting there to help me put the graph in the right spot. And so here's our final graph like this. And this would be the negative square root of x plus 3 plus 5. All right, and so that's our transformed graph there at the end. All right, so some really, hopefully some good examples here for you to go back and look at function transformations. And so now that we've talked about transformations, what we're going to do for much of the rest of the semester, so for most of the rest of the semester, we're going to turn our attention to 4 very specific categories of functions. And so we are going to turn our attention for the rest of the semester to polynomial functions. That's what we'll spend the most time on. And then rational functions. Spend a day or 2 on rational functions. And then exponential functions. It'll be a long time before we get to exponential functions. That'll be April before we get there. And logarithm functions. And for most of the rest of the semester, that's what we're going to be dealing with. We'll have to take a few detours here as we go along there, but that's our goal for the rest of the semester is to deal with those categories. Now, polynomial functions is a huge category. And so let me, what I want to do is kind of set this up with polynomial functions. And with polynomial functions, it's in our textbook section 4.1 and then chapter 5 up through section 5.4. So 5.1, 5.2, 5.3, 5.4. Now, polynomial functions can be categories like this as first degree functions. Those are functions that are frequently written in this form, f of x equals mx plus b. Those are what we call linear functions. But those are really first degree polynomial functions. And the graphs for these are always lines. All right, and then we look at second degree, and so that's what we will cover in section 4.1 of your book. Second degree polynomial functions are functions like this: f of x equals ax squared plus bx plus c. Right, and the graphs for those are always the same. Graphs are always parabolas. And then we're going to look at degree 3 or higher. And that's where we're going to spend most of our time overall. And the graphs here are more complicated, basically, is the way to say that. And so that's going to take us some time to get through that. So what we're going to do in this class is when we come back on Monday, we will be dealing with the first two lines, which I consider that to be mostly a review for you as college algebra students. This is mostly review. And then second degree parabolas, I expect that some of you have seen that in high school. And so some of you have some familiarity with second degree functions and parabolas. What I'm going to do is generally develop that kind of from the beginning, but there's just not a lot to cover there. So generally, and so we'll get through that also. And so first and second degree equations, polynomial functions, we will deal with Monday when we come back. And then after that, we'll get into degree 3 or higher. So that's kind of where we are headed for the next couple weeks of the semester. So, all right. Does anybody have, any of you who are with me live today, do you have any questions about anything?
I'm good.
Okay, then everybody have a great day. And